Hello, and welcome to my Lab 3 video report, where I will calculate the mass of a black hole given the position and mass data of a star orbiting it, as well as the black hole's position. The idea is to take the position data of the star's orbit and apply the definition of velocity and Newton's second law in order to compute the net force that the black hole has on the system, which is the star. With the net force and the distance calculated, the data is used with Newton's law of universal gravitation to compute the mass of the black hole. Since the computation is tedious by hand, VPython will be used to calculate the net force at each time interval of 1 Earth day. The parallel and perpendicular components of the force will be calculated in order to observe the forces acting parallel to the motion and perpendicular to the motion in VPython. The mass of the black hole was computed to be 2.7899 times 10 to the 31st kilograms. Lastly, I'll discuss whether the identity of a new black hole can be distinguished if all of the other variables remain constant, and I'll also discuss the differences between Fnet and dp dt. Newton's second law will be used to relate the change in velocity to the net force. Newton's universal law of gravitation will be used in conjunction with Newton's second law to compute the mass of the black hole, since g, the star mass, r squared, and Fnet are known. The definition of velocity will be used to relate the change in velocity, as in Newton's second law, to the change in position. From the position data, velocity needs to be calculated. The velocity can be calculated by taking two adjacent position data, subtracting the position points, and dividing the difference in position by the time step delta t. This can be done between every two data points in the entire position data to compute the velocity at each time step. Momentum is defined as mass times velocity, so multiplying all the calculated velocities by the mass of the system will result in momentum values as shown below. The change in momentum over a change in time can be calculated as follows: dp over dt equals to p2 minus p1 over delta t. The unit vector that points in the parallel direction of the momentum is p1 hat equals to p1 over the magnitude of p1. The parallel component of the change of momentum can be computed as the difference of the magnitudes of the two momentums divided by their time interval multiplied by the unit vector, as shown below, which is magnitude of p2 minus magnitude of p1 divided by delta t times the unit vector p1 hat. Since the total change in momentum and the parallel component of the change in momentum is known, the perpendicular component is the difference between the total change in momentum and the parallel change in momentum, as shown below, since the sum of the parallel and perpendicular components equals to the total change in momentum. Since doing this iterative computation is tedious by hand, you will use VPython to iteratively calculate the changes in momentum at every point of the star's orbit. The orbit of the star around the black hole is shown. The green line is the path of the star. The black arrow is the parallel component of the change of momentum. The blue arrow is the perpendicular component of the change in momentum. The yellow arrow is the total change of momentum. At this moment here, the perpendicular component is completely equal to the total change of momentum, and the parallel component of the change of momentum is 0. After this point, you can see that the parallel component of the change of momentum is opposite of the change of momentum overall. The values printed out here is magnitude of the net force at each time interval. This value down here is the net force that will be used to calculate the mass of the black hole, which is also shown down here. Since the model here uses the same procedure as described earlier to iteratively calculate the net force, it does a very good job calculating and predicting the motion of the star. The magnitude of the net force on the star at its last point of its orbit is this value here. The vector distance between the star's position and the black hole at the last point of the star's orbit is this value. The position of the black hole was known, and so is the last point of the star's orbit, so the difference of the two position points can be used to calculate the vector distance. The magnitude of the vector distance squared is this value, which will be used in Newton's law of universal gravitation. Rearranging Newton's universal law of gravitation, the mass of the black hole is isolated to the left side. Plugging in the numbers, the mass of the black hole comes out to be 2.7899 times 10 to the 31st power kilograms. Can the mass of the black hole change if all the other variables change? Well, if the black hole's position is the same and the star's orbit is the same, then the distance between the two is still the same. The star's mass does not change since it's the same star still. G is a universal constant, so that never changes. The only thing that could change the mass of the black hole is the magnitude of the net force. Since the motion of the star is exactly the same as before, even this does not change. Therefore, according to Newton's law of universal gravitation, the mass of the new black hole has to be the same as the original black hole. It is impossible to tell the difference between the two. How is the net force F net different from the change of momentum dp dt? Conceptually, there are different entities. The net force is the sum of all the pushes and pulls that act on the system from the surroundings. The change of momentum is a change in velocity or an acceleration that the system is experiencing. However, mathematically they are the same through Newton's second law, F net equals to dp over dt. The same idea applies for parallel and perpendicular components respectively. Newton's observations and countless experiments in kinematics have proven this equation to be true. It has never been disproved in kinematics. This is the end of my lab report. Thanks for watching.